Okay, good morning, everyone, and welcome to Lecture 13 of 124105, where we will talk about magnetic properties of matter. It's sort of ties in with what we learned so far, because in the last lecture, we started to talk about what creates magnetic fields in the first place. Of course, in the very first lecture, we learned that magnets create magnetic fields. And in the last lecture, we learned that if you have charges that are moving, these charges will create a magnetic field around themselves. We already learned that current is essentially just charges that are moving, right? So if you have a moving charge, then that moving charge will create a current. And if moving charges create magnetic fields, then therefore currents create magnetic fields as well. And you can observe this experimentally if you have a wire and you let current pass through this wire. Put some compasses around the wire. The compass needle is, of course, a small magnet, and you will see that the compass needle, or in essence, the magnets, align around the current carrying wire, showing you the direction of the magnetic field that's created by the current that is flowing through the wire. Okay. And in our last lecture, we derived the equation that gives us the magnetic field that is created by a current I, that is flowing through a straight wire. Right? We used Ampere's law in the last lecture to derive this equation here for the magnitude of the magnetic field. And then we learned that for the direction, since it's experimentally observed that the magnetic field forms circles around the current carrying wire, we use the right hand grip rule to find the direction of the magnetic field, right? Where you point your thumb in the direction of the current and your fingers curl in the direction of the magnetic field. So hence in this illustration here, the magnetic field lines are circles. And in this straight wire configuration here, if you point your thumb in the direction of the current, your fingers will come out of the plane or the page above the wire. And below the wire, your fingers will enter the page or the plane. Hence, you have two directions for the magnetic field, one above the wire coming out and one below the wire that's going into the page or the plane. Okay. And so we see here that if you have a current, this current will create a magnetic field around itself. Hence, it makes sense that if you put another wire, right? If you put another wire beside this current carrying wire, and this other wire also carries a current, this second wire will create a magnetic field around itself. And therefore, these two wires will exert a magnetic force to each other, according to this equation here. Because in order to have a magnetic force, you need to have a current and a magnetic field. And these two wires that are beside each other, they both carry currents, and those currents they carry create magnetic fields around themselves, right? And we learned that last time. In fact, if the currents are going in the same direction, then the force exerted by the wires on each other are attractive. Okay? And if the currents are flowing in opposite directions, then the force that these currents exert on each other are repulsive. Right? Okay. And we compared that to the force exerted by magnets. We can see here that for magnets, like poles repel, right? So that a north pole will repel a north pole. But opposite poles attract, such that a north pole will attract a south pole. So if you compare the direction of the forces in a magnet, right, opposite poles attract, whereas for current carrying wires, oppositely flowing currents will repel each other, right? So they're sort of opposites of each other. right? But here, the key idea I wanted to illustrate is that if you have a wire and that wire carries a current, then that wire will create a magnetic field around itself, such that if you take the wire and coil it so that you form a circular loop as such, as shown here, and you apply a current through the wire. Okay, so watch closely. So you have here a wire, and these are iron filings around this wire loop. Okay, current will be applied through this wire, and watch closely what will happen to the iron filings when current flows through this circular loop. Okay, so you can see there the iron filings aligning themselves. Yeah. I think it's a bit bright. So, but can you see how the iron filings align themselves? So the aligning of these iron filings indicate that when current flows through this wire loop, then magnetic field is created, and the magnetic field lines are indicated by the aligning of these iron filings. Okay. Of course, the iron filings don't have arrowheads themselves that tell us, the direction of the magnetic field created by this wire loop, but we sort of use the convention to find the direction of the magnetic field created by the current in the wire loop. We use the same convention we used, right? For a straight wire, say just for a straight wire that's carrying a current, you point your thumb in the direction of the current, and the magnetic field lines curl around this wire loop. So you can sort of do the same technique with the wire loop, except that you have to determine the direction of the magnetic field at every point, because your wire loop is, of course, circular. So the current direction is changing at every point along the loop. So say at this point your thumb in the direction of the current, and your fingers curl, right, showing you the direction of the magnetic field. So at this point, the magnetic field is going upwards inside the loop, and outside the loop, your magnetic field lines will be pointing downwards. Right? Again, if you look at another point along the loop, point your thumb in the direction of the current. Say your current is flowing anti-clockwise like this, then your fingers will again point upwards, giving you the direction of the magnetic field inside the loop, but outside the loop, your fingers are pointing downwards. So the magnetic field is still like forming circular loops around this coil of wire, except that, the current direction changes at each point along the loop. But notice how even if the current is changing a direction around the loop, the magnetic field lines are always pointing upwards inside the loop. Yeah, inside the loop, the magnetic field lines are always pointing upwards. Good, makes sense? So if we draw the magnetic field lines of a loop that's carrying some current, we draw it like this. So inside the loop, you have magnetic field lines that are always pointing upwards. Of course, these magnetic field lines, they form closed loops. It's just not, but they do form closed loops like this, so that inside the loop, the magnetic field lines are pointing upwards, and outside of the loop, the magnetic field lines are pointing downwards at each point. Okay, so for loops, we can sort of change a little bit how we find the direction of the magnetic field. For a straight wire, it's like this, right? Point your thumb in the direction of the current, and your fingers curl in the direction of the magnetic field lines. But for a loop, because the current is changing at each direction, it becomes tedious to find the direction of the magnetic field at each point. So for a loop, what we can do is instead to curl our fingers in the direction of the current flow. So if your current is flowing in this direction, curl your fingers in the direction of the current flow, and your thumb points in the direction of the magnetic field. So it's we just change the orientation. As written here, right hand grip rule for loops. You curl your fingers around the loop in the direction of current flow, and your thumb points in the direction of the magnetic field. So it's now easier. You don't have to orient your thumb at different directions at each point, but rather just curl your finger in the direction of the current, and your thumb is pointing upwards, meaning the magnetic field lines are going upwards in from the middle of the loop. Good. All right. So if we look at this, the magnetic field lines of this wire loop, okay, this is a wire loop. Again, the wire loop is oriented this way, and the current is flowing in this direction, right? So if we curl your fingers in the direction of the current, notice how your thumb is pointing to the right. So you have here the magnetic field lines going out of the loop or going to the right at this end of the loop. And of course, it forms closed circles. So magnetic field lines always form closed circles around a wire. And so it forms a closed circle and it enters the other end of the wire loop. Right? So you have here magnetic field lines coming out on the right side and magnetic field lines entering the loop on the left side. Okay? It's sort of, if we assign, right, we said before that magnetic field lines leave the north pole of a magnet and enters the south pole of a magnet. Right? As you can see here, this is a bar magnet. Right? We drew the magnetic field lines in the very first lecture such that the magnetic field lines come out of the north pole, they form closed loops, and they enter the south pole of the magnet. If you compare the magnetic field lines of this magnet to the magnetic field lines of the loop, the wire loop, you can see that they're very similar, right? So what we can conclude from here is that the wire loop that's carrying some current sort of acts like a small magnet. Right? It creates a magnetic field. The wire loop that's carrying a current creates a magnetic field, and it sort of acts like a small magnet which has a north pole and a south pole. The north pole is that end where the magnetic field lines leave the wire loop, and the south pole is the end of the wire loop where the magnetic field lines enter that wire loop. Good. That makes sense. Yeah. Yep. So keep that in mind, because in the next lecture, we will be using this a lot, assigning north poles and south poles in a current carrying loop. Right. But then we can also take several loops. So this is just one loop of wire or many loops, but bunched up into a single loop like this. But we can take several loops and place them close to each other, in which case we have this configuration, which we call a solenoid. Right? And notice how, again, you have iron filings around these solenoids, a collection of wire loops. If we pass a current through the solenoid, notice what will happen to the iron
tap a key
filings.
and see what happens.
Right. It's probably not as obvious, but
Right
can you see
at the other end? Still getting a bit of looping
how
around the
the
edge
iron
there, but it's not
filings
joining
are
up.
sort of aligned around here, and maybe it's more obvious around the corners or the corners of the solenoid here, where you have
Okay, so we'll zoom back out.
some curving of the iron filings
Just have
there.
a quick look at all the displays again. So our 5 coils.
Can you see that, or it's not so obvious? Sort of.
We can compare that to the.
Yeah. So if you compare, this is the single wire loop. You have There, the iron filings aligning, showing you the magnetic field lines through the loop. And for the solenoid, which is just a collection of this wire loop essentially that's placed close to each other, hope you can see the iron filings aligning themselves in the middle here. It's probably not so clear. I probably try to turn off. Did that help? It's not so obvious. Yeah, it's not so obvious, but there's some align, the iron filings sort of align themselves right inside the solenoid, so in the middle of, so it's sort of a collection. It's the same as this single wire loop, but it's just a collection of this single wire loop. So you would expect the magnetic field lines for each of these wire loops will be sort of like these straight lines inside each of these wire loops here. So if we draw the magnetic field lines of the solenoids, right? This is the solenoid cross section. So each circle here is the wire loop, right? And you sort of cut through it. So you're looking at the cross section of each of the wires making up the solenoid there. And notice how the magnetic field line is concentrated inside the coils of the solenoid. And if this is the solenoid, each wire carries a current. Okay, if you can see, you have their dots and dots above and then excess below. That means current is going out of the page here, above the top part of the solenoid, and then current is going into the page at the bottom part of the solenoid. If we do a right hand rule, so we curl our fingers in the direction of the current flow. Current is flowing such that the current is going out of the page at the top part of the solenoid and going into the page at the bottom part of the solenoid. Hence, the magnetic field direction inside the solenoid is pointing to the right, as we can see here. So we can see that at this end of the solenoid, the magnetic field lines are leaving the solenoid. Of course, they will form closed loops. It's just cut because there's no space, but that continues through connecting to this magnetic field line, right? So at this end of the solenoid, magnetic field lines are leaving, form closed loops, and they enter the solenoid at this other end of the solenoid there. Okay, so what we can see is if we again compare that to the magnetic field lines of a bar magnet, okay, it's again similar. For the magnet, you have magnetic field lines leaving the North Pole, forming closed loops and entering the South Pole. We can see that for a solenoid, we can again assign a North Pole. This is where the magnetic field lines leave the solenoid, and the South Pole, which is the end where the magnetic field lines enter the solenoid. So again, your solenoid sort of acts like a magnet, a bar magnet, when you have current flowing through the wires making up the solenoid. Right. Okay, and last time we saw this equation for a solenoid. The magnetic field is equal to mu naught Ni over L, where N is the number of coils or number of loops of wire, right? So each coil here, that's N equals 1, let's see, 1, 2, 3, and so on. So each coil will contribute to N, the number of loops or coils in your solenoid, and L, that's the length of the solenoid. So it's this actual length, right? It's that actual length of the solenoid rather than the length of the wire that's used to create that solenoid. So it's the actual L is the actual length of the solenoid. Mu naught, it's a quantity called permeability of free space meaning air. Okay. And for air, the permeability is equal to this number, 4 pi times 10 to the negative 7. But the permeability can also be changed. It's a property of the material. Okay. If you put a different material inside the solenoid, then the value of mu will change, taking up the value of the permeability of that material. And it's it's a property of the material that you can look up in some tables. But what this tells us is if you put a material inside the solenoid, then you can influence how much magnetic field is created by that solenoid that's carrying a particular current I. Okay. And we can actually combine those two concepts, right? So we saw here that a solenoid that carries a current sort of acts like a magnet. And then if you put some material in the center of the solenoid here, you can influence how much magnetic field is created in the solenoid. And that essentially is how electromagnets work. So this is a very common illustration of an electromagnet. Get an iron nail, right? Get a wire, coil it around the iron nail. Essentially what you're making is a solenoid, right? When you take a wire and coil it around the iron nail, you're making a solenoid. You have loops of wire that are closely spaced together. That's your solenoid. And then the iron core, right, that's the inside of the solenoid. The iron core has a particular permeability mu that is very high. It's higher than the permeability of free space. So you are essentially increasing the magnetic field that's created by your solenoid once current is flowing through your solenoid. Okay. And as we have seen, if current flows through the solenoid, say if the current is flowing in this direction, right? Flowing in this direction, in this direction here, it depends. Yeah, if your current will flow in that direction, then this will serve as the north pole of the solenoid, south pole of the solenoid, because your magnetic field lines will be directed this way according to the coilings, right? So if your wire is your current is flowing like this and your wire is coiled in this orientation, the magnetic field lines inside the solenoid will be directed to the right. That forms the north pole and that forms the south pole. So in essence, you have formed a magnet. Okay? And this is just a giant electromagnet here that's used in the scrapyard, using exactly the same concept as this electromagnet here connected to a battery. Right? So then you have a big magnet that then attracts the iron or the metal in the scrapyard. Good. Does that make sense so far? Right. So far, what we have learned is that currents create a magnetic field. Right. If you coil the wire, then you create a solenoid. If you put a material in the core of the solenoid, you're influencing how much magnetic field is created. Right. So the key idea here is that currents create magnetic fields. Okay. Right. But the question remains, right? Why are magnets magnetic? Right? Why are some materials magnetic? Right? Like, why is a bar magnet magnetic? What we have learned and discussed so far is that if you have a current, if you apply a current on a wire, that wire becomes magnetic. But how about a magnet, a bar magnet that's by itself? There's no current flowing through that magnet. Why is that magnet magnetic? And why is it that only certain materials can become magnets, and why is it that wood will never become magnetic? Have you ever wondered about that? Probably not. But we will learn why magnets are magnetic. Well, still the key idea is that moving charges create magnetic fields, right? The reason why a current carrying wire becomes a magnet is because current is the moving charges, right? You have charges that are moving that create this current, and therefore currents create magnetic fields. So the very key essence of producing magnetic fields is moving charges. Whenever you have moving charges, you create magnetic fields. And if we look into the atomic structure of a material, you have, of course, the nucleus, which is positively charged because it contains the protons. But you have the electrons that are orbiting around the nucleus. So in essence, in the atom itself, you have an electron that is moving. An electron is a charge, right? Hence, if you have a moving electron, okay, that's orbiting around the nucleus, that is very close. Essentially, it's like a current flowing through a loop. Okay? And as we've seen earlier, if you have a loop and current is flowing through the loop, curling your fingers in the direction of the current, your thumb points in the direction of the magnetic field. So it's sort of also what happens with the electron that's orbiting around the nucleus. If the electron is orbiting in the anti-clockwise direction, then you have a magnetic field that's created by that orbiting electron. You have a magnetic field that's pointing upwards. And the magnetic field created is indicated by this magnetic moment there, it's the same magnetic moment that we learned previously. The magnetic moment describes the magnetic field created by the moving electron here. But at the same time, right, as the electron is orbiting the nucleus, it's also spinning around its own orbit. So there are two kinds of motion here for the charge. You have the orbiting of the electron, and at the same time, you have this spin as the electron spins around its own orbit. Okay? Again, the key idea is whenever you have a charge that's moving, it creates a magnetic field. So even the spinning of the electron will create a magnetic field. Depending on the orientation of the spin, you curl your fingers in the direction of the spin, and your thumb points in the direction of the magnetic field that's created by the spin. So in this case, the magnetic field is pointing upwards, and it's indicated by the magnetic moment mu. Right. So in a magnet, which has, of course, electrons, it's the movement, the orbiting of these electrons and the spinning of the electrons that makes that magnet magnetic. But why is it that some materials are not magnetic? It's because in a material you have many atoms, right? And which means you have many electrons. And each electron is spinning around the nucleus, and each electron is also spinning around its own orbit. Now, if the electrons are moving in random orientations, so that you have spins in opposite directions, then the magnetic fields created by these opposite spins will cancel each other out. So say here you have two electrons, one is spinning anti-clockwise and one is spinning clockwise, right? These opposite spins will create magnetic fields that are opposite in direction, and therefore these magnetic fields cancel each other out. And when that happens, you have an overall magnetic field equal to 0. And that's why those are materials that are not magnetic. For example, wood or plastic or any non-magnetic material there. Good. Right. Right. So based on the properties of material, therefore, right, based on the number of electrons and how electrons spin in a material, we can classify materials into three types: diamagnetic, paramagnetic, or ferromagnetic. And we'll discuss each of these types of materials, what's different between them. Okay, it's all to know what's different between them. We have to look at what's happening to the electrons and the magnetic moments in these electrons in the atoms of the material. So for a diamagnetic material, initially you have electrons that are spinning, so that their spins are oriented randomly initially without an external magnetic field. Their electrons are all spinning, so that you have this random orientation. But if you immerse the diamagnetic material in an external magnetic field, so say if you put it close to a magnet, or if you apply a current through this diamagnetic material, what happens is that the electrons align themselves so that the spins are all aligned, but they are aligned in the opposite direction as the external magnetic field. Okay. Right. You have, therefore, oppositely oriented magnetic fields, which will create magnetic forces that will be opposite, and therefore they will repel each other. So these are diamagnetic materials. The key feature is that their orientation, the aligned orientation of the electron spins, are opposite the direction of the external magnetic field. For a paramagnetic material, it's the same as the diamagnetic materials. The electrons are randomly oriented initially, just the material by itself without subjecting it to an external magnetic field. So overall, the magnetic field of that material is zero. So that material is not magnetic because the electrons are oriented randomly, canceling out each of the individual magnetic fields created by each of the electrons. But if you immerse this material in a magnetic field, say put it close to a magnet or apply a current through this paramagnetic material, what happens is that the electrons align themselves so that their spins align, and they align in the same direction as the external magnetic field direction. Okay. So you have the same orientation of magnetic fields in the electrons as the external magnetic field that reinforces the overall magnetic field. And also you have magnetic forces that are in the same direction, and therefore these materials are attracted by the external magnets. Right, so those are paramagnetic materials. And finally, ferromagnetic materials. They're quite different from diamagnetic and paramagnetic materials. What's different about them is, right, for diamagnetic and paramagnetic materials, you have electrons that are spinning in random orientations. But for ferromagnetic materials, you have electrons that are spinning in the same directions, right? So you have, so these arrows here in this drawing indicate electrons with the same spin, okay? And we call these magnetic domains. So areas in the material which contains electrons that are spinning in the same direction, they are called magnetic domains. So this is a magnetic domain. All the electrons in this magnetic domain are spinning in the same direction, such that they create a magnetic field that's downwards. So we can say that, yeah, all the electrons in this magnetic domain, or in this part of the material, they're all spinning in the clockwise direction, so that their magnetic fields are all pointing downwards. Okay. Whereas in this magnetic domain, or this part of the material, you have many electrons that are spinning in the anti-clockwise direction, so that their magnetic field lines are all pointing upwards. Right? So initially, you have many electrons. So you have, for example, groups of electrons, like factions of electrons, understand each other, and so they create the same magnetic fields. But there are different groups of those electrons, and sometimes each group is spinning in random orientations. So you have magnetic domains with random orientations. Overall, the total magnetic field of this material, ferromagnetic material, can be zero, because you have, even if you have electrons that belong to one group, to one magnetic domain that's spinning in the same orientation, overall you have magnetic domains with different orientations. So overall, the magnetic field is zero. But then if you subject this ferromagnetic material in a magnetic field, in an external magnetic field, say, for example, you bring this ferromagnetic material near a magnet, like here, or if you make a current flow through this ferromagnetic material, okay, what happens is that the random orientations of the magnetic fields in each magnetic domain then align themselves, right, according to the external magnetic field. So you now have a better alignment of the electrons in the magnetic domains. And then this ferromagnetic material then becomes magnetic, right? So like, for example, this iron nail is an example of a ferromagnetic material. You bring it close to a magnet, its magnetic domains align themselves according to it. The south poles of the electrons are attracted to the north pole of the magnet. The nail becomes a magnet itself, okay, which then influences the second nail to align their magnetic domains according to the magnetic field of the first nail. So the north pole of the first nail attracts the south pole of the electrons in the second nail. The second nail becomes a magnet. Right? The magnetic fields in the second nail influences the magnetic domains in the third nail. The electrons in the third nail align themselves so that the north pole is attracted to the south pole of the second nail, and so on. Right? So in a ferromagnet, sort of, the iron nail becomes magnetic, or the material, the ferromagnetic material becomes magnetic if you bring it close to an external magnetic field, like a magnet or a current. Right. Okay, so those are the three kinds of magnetic materials. Again, the difference is atomic. It's how the electrons spin and orient themselves. But I found this video, which is a very interesting video, and it sort of illustrates the differences between the three materials. So hopefully the sound works. Let's see. And I probably need to, let's see, hopefully.
You're probably already familiar with You're probably already familiar with ferromagnetism. Ferro means iron. An unmagnetized piece of iron, or nickel, or cobalt becomes a You're probably already
There's
familiar
a
with
lot of delay,
ferromagnetism.
so there's a lot of delay, so I'll just repeat this.
You're probably already familiar with ferromagnetism. Ferro means iron.
Oops.
An unmagnetized piece of iron or nickel or
I'll echo. I'll go to the backup and use this. We want to pause this. It's sufficient for us to know for our course the reason behind why materials are magnetic and why some materials are not magnetic. And at the heart of it, it's the movement of charges, right? It's either moving charges creating currents that therefore create magnetic fields, or even without the presence of currents, it's the electrons moving around the nucleus and spinning around their orbit that makes up the atoms of materials that create magnetic fields, such as that such that what's making bismuth and a bar magnet magnetic. Yeah, so today's lecture is actually quite conceptual. This is probably the only lecture where we don't have any calculations. So it's hopefully quite a light lecture. So we'll end the lecture here, and tomorrow we will talk about how magnetic fields will create current and how wireless charging works. So have a good day, everyone, and I'll see you in the lecture tomorrow.